Did we leave off at the very end? We were talking about the existence of Nash equilibria, and I just sort of pointed out that the proof as we presented it, it's not constructive. If we use the similar formulation, if we could find a fixed point, we could get a Nash equilibria for free. That part was constructive, but how do we get a fixed point? Now, this is the general phenomena for most known proofs about the existence of Nash equilibria, even a different kind of proofs. They tend to always use this sort of a fixed point type object, okay? A type of object that we do not really know how to find efficiently. So, and that then therefore, does it mean that we cannot find a Nash equilibria under any circumstances? Well, there is no reason to believe that, because you can have a game which is very precise, like which is defined in a particular way, for which you can compute Nash equilibria fairly efficiently. So, obviously, when we take small games like rock, paper, scissors, those matching pennies and all those sort of toy examples we saw, we could see that we can compute, we can sort of understand what the Nash equilibria would look like. So, now we will talk about a more general game, okay? The type of game that captures lot of scenarios, but still it has a fair amount of restrictions, and in that setting we are able to find a Nash equilibria, and it does not require the type of fixed point theorem that we saw before. Okay. All right. So, what is a zero sum game? A zero sum game is one where the outcomes of the two players, in this case it does not have to be a two player, actually it could be any number of players, but the idea is the payoffs of all the players taken together adds up to 0. So, payoff of any player for a given strategy profile adds up to 0. That is what a zero sum game literally means. You could have a more generalization of this, which is a constant sum game, where the payoff adds up to a constant, but that can be reduced to the zero sum game scenario. It is not very particularly hard and so on. So, primarily we tend to study zero sum games, because that allows us to answer questions about the constant sum games. So, as you can see, so in rock, paper, scissors, it is naturally a zero sum situation, because if both people are playing rock, both of them adds up to 0, and if you are playing any other two distinct strategies, then of course one is a winning strategy, other one is losing, and so this is a natural example of a zero sum game. Okay. So, can you tell me, if this was a situation where people were taking turns, okay, do you think going first would be going first or second, one or the other gives an advantage? Which is better? Why? Correct. Over here it is trivial. Can you think about but the idea remains the same, that you can adapt your strategy purely based on what the first player did, right, like in an answer response mechanism. Okay. So, then does it mean that the first player had absolutely no winning strategy? No. Why?
Like in most of the games, X and 0, the one who generally plays has the lead as such.
A little louder.
Like the one who is playing first, then he can influence how the game also goes, like by playing the move that he wants to do first.
But the second player can always answer with an optimal move tailored to whatever the first player did, right? That is what you also told me, that the second player is at no disadvantage.
I do not know exactly, but I know that in this X and 0 game, the one who goes first.
What is X and 0 game?
Like X 0, you make a great.
Oh, so in that the first player who goes, that person has an advantage.
Yes.
Okay, that is a one particular specific example, but I am saying that any type of a answer response game, does going first give, is it always like, so you gave an example of a game in which going first may provide you with some advantage, right? Okay. So, that is it the case that the second player has no chance?
No.
Okay. So, now if I thought of if I were to ask you about a more general kind of game, not that tic tac, but some other game. What do you think should be the case? Like, does the first player, can we say anything meaningful about the strategy of the first player? Maybe not as obviously, but can there be other strategies also? If such a thing, if it did not give an obvious advantage, but still could we still reason about it? Not sure if the question is phrased properly. Okay, fine. Let's see. So, we agree that the second player does not actually have to use randomness at all. He can just look at all possible actions he can play as a response to whatever the first player is doing, right. The first player could be playing a mixed strategy. He basically looks at all the outcome, all the possible actions he can respond to, like we saw before, and find the one that maximizes his payoff and respond with just that, right. Okay. So, the second player requires no randomness. Now, the question is, can the first player use randomness to his advantage? In any sort of a two-player game, is it the case that the first player will always have a randomized strategy by which he can safeguard his interest?
Here, for every action, there is an action that beats it. That is why the second player has an advantage. Like if there is a rock, then the other player can always play a paper to beat it.
If it were a more general game, like for example, take any of those battle of the sexes and all. If the boy goes first, he declares whatever his interest is. The girl sees that I might as well just match it, right. So, the girl can always respond with one single action, pure strategy, which will maximize her outcome. That argument works generally for all games. Second person does not need any randomness. Question is, can the first player actually use randomness for their benefit? It turns out, in some cases, the first player may be able to safeguard his interest that way. In particular, in a two-player zero-sum game, it turns out that the first player has an optimum strategy, a mixed strategy at the very least, that he can play, that will ensure that no matter what the second player does, he can get the best possible outcome for himself. Okay? That is what the min-max theorem says. Now, I will explain what this means in math form, but is the statement clear what I am trying to say? That the second player can always has a winning strategy, and that is deterministic, but the first player situation is also not sunk. First player can use there exists a mixed strategy that the first player can use that will safeguard his payoff. Okay?
So, what is meant by safeguarding?
Safeguarding means that the response, whatever response the second player does, it will not drop his optimum value beyond this. So, for example, the rock paper scissors situation, whatever the first player plays, if it uses deterministic strategy, the second player responds with the strategy that would beat it, right. But the question is, can the first player play a mixed strategy such that no matter what the second player does, it would still give him the optimum outcome from that game. What that optimum outcome is, that we will talk about, but this is the theorem that it says that the first player, there exists a strategy that the first player can play, which will ensure that he gets his optimum value. Okay?
So, in the scenario 1, then like so here in both the scenarios, are we assuming that the player 2 is playing after player 1?
When I am saying player 2 or the second player, that is what I mean. So far, I have not yet stated what this theorem means, because there is a lot of notation, and I will explain what it means. But when I am saying second player, I mean the person who goes second, okay, like an answer response sort of a situation. Okay? All right. So, a two-player zero-sum game is often specified by a matrix A, that is the payoff matrix for the row player. Okay? So, okay, just a minute, because I do not have my keynote. So, okay. So, this theorem that I just now said, that for a two-player zero-sum game, there exists a strategy, okay, for the first player by which he can ensure that he gets an optimum outcome is also the Nash equilibrium strategy, and how it is we will see was proved by John von Neumann in 1920, long before game theory the way we understand it came to be. Sorry, yes, he proved it in 1920, and he was arguing, and his initial proof involved again a fixed point theorem, but later on subsequently, as the proof that we will see today uses linear programming framework. So, how many of you are familiar with linear programming, or at least have seen it? Oh, that is very good, lots of people. So, this proof, this theorem has been rediscovered many times in different ways, okay? And the proof that we will see today uses this linear programming duality property, and it is probably the most cleanest and easy to understand. Okay, maybe that is arguable. So, the theorem predates the technique, okay. Sorry. So, what is a zero sum? How do we represent the zero sum game? So, each game here, it is a 2-player game. So, we will define, I think some slides are missing, sorry. So, there are 2-player game. So, it is a 2-player, player 1, player 2, and A is a payoff matrix where each row in this index represents a strategy chosen by a row player. I don't know what's that. Okay. And the column player response is basically indexed by the columns. So, it is no different than what we saw in the rock paper scissors or matching pennies and over there the matrix was a bit of weirdly, each entry contained 2 values and so on. Okay. But for a zero sum game, we can just represent the payoff of one player, and the payoff of the second player is understood basically the negative of that, right. So, just one matrix completely specifies the payoff of both the players. Okay. So, when we have a matrix, let me just, yeah. So, let us see this. So, you have a matrix like this is a 4 cross 3 matrix. Each of these row entries represents a strategy, and the row player picks one of the strategies, and the column player picks one of the strategies which are the column indices. The entry that is stored here, so suppose the row player picks this row, third row, and the column player picks the second column. So, the row player's payoff would be whatever is stored in this entry, and the column player's payoff would be negative of that. Okay. Okay. So, now with this sort of thing in mind, let us just go back to the previous thing. Okay. So, what this says is, here x is again a vector, stochastic vector representing probability distribution of the, so x is indexed by x1 to xm. So, here the notation is slightly different, but still I mean it is conceptually it is similar, but over here x is a row player's strategy. Okay. So, the values here tell you what is the probability that he picks row 1, row 2, row 3 and so on, and the column players similarly it is let us say y n. Okay. Here n, m and n represents the 2 strategy sets of the 2 action sets of the row and column player, and not n does not mean number of players. Now, we are talking about only 2 player games. Okay. So, that is the thing. Okay. So, this says that if the row player goes first, how, okay, just tell me, if the row player is going first, the column player does what? Just use this ideas that we just now discussed a while ago. The column player should just basically respond with a column such that he sees, and okay, sorry, when I just talk about x transpose A y, it is basically linear algebra, I just assume that. This tells me payoff, can you tell me what does this say? Payoff of whom? X is a probability vector, A is a payoff matrix and y is another probability vector. What does this, what should this quantity represent? It says payoff, remember A is the payoff matrix of the row player, right? Payoff of row player if row player plays X and column player plays Y, correct? So, if that is the case, then what is the payoff of the column player? Yes, just that. Everything remains the same, right? So, you see that there exists a simple, very straightforward relationship which the players can use to argue about what they should do against the other person. If the row player wants to win, it tries to maximize this quantity, right? The column player knows this. If the column player is going second, right, it should try to do whatever it can to keep this value low as possible, right? Yes or no? Because if it is low, then his payoff will be higher. Okay? This is where this minimax term comes in. If one person is trying to maximize, right, the other person should respond with a minimizing strategy such that, and the place that all these things come to, like they become equal, their basically their strategy is stabilized, literally is the sort of, not literally, it is that equilibrium point. Okay? So, that is the intuition. So, what this equation says is the following. So, the row player picks some, so it is clear that a row player should really try to find strategy X such that he does not yet know, he is going first. He does not know what the column player will respond with. However, he knows that the column, whatever I play, column player will respond with a Y that will minimize my payoff, correct. So, the row player can actually do this calculation ahead of time and respond and find the strategy that X that basically maximizes this minimizing quantity. Okay. Now, if the column player goes first, what should be his thinking?
That every move that X is making, he is trying to maximize this quantity.
Yes, that is the column player understands this. So, the column player should do what then?
He has to minimize the.
Yes, because again this X T A Y tells me the payoff of the row player because of the definition of A. But the column player knows this, that I need to keep this value as small as possible, that automatically maximizes my thing. So, that is why he will find the Y that among all the X's that the row player can find, it will give you the lowest possible value. Okay? Now, min-max theorem says that these two values are actually the same. We argued very differently, like who goes first and who goes second, and row player going first or the column player going second. Turns out min-max theorem says that they are actually the same thing. Like both of them, if they play optimally like this, no matter who goes first, the same value would be attained. Okay? All right. Somebody said something?
X is like, it should be a like column vector, right? For X transpose A by 2.
If I X is usually, so X, when we write this notation,
So this
vectors
X
are
is
usually
actually
written
X
as column vectors, but X transpose, in order to do matrix multiplication, I need X to be this, A is this and Y is this. Vectors are usually not written like this, right? It's a linear algebra notation, nothing more.
So the way we have written x1 till xn, that could be x transpose, right?
Yeah, that itself could be extra. Okay, yeah. Okay. So, and you can see why this is the correct thing. This is basically telling me the probability that row player picks row 1, row 2, row 3, row 4, row 5. Each of these columns are saying what? That what would be the payoff of the row player, right? If this thing gets picked, the first row or the second row, third row, assuming that the column player responds by this, right? This particular column. So, that is why. Okay. All right. So, so we now, so given that these row vectors represent mixed strategies, right? Because they are I mean this is a distribution, they sum of to 1 and so on and so forth, it is inherent in this. What can we say about the payoff of the row player? The Aij thing, payoff when row player action is I and column player's action is J. But we saw how we can extend this idea of payoff, right, based on action choices onto a the expected payoff when mixed strategy is used. The same principle appears here also. You unravel the definition of expectation, you will you sum over all possible choices are I and J. So, Aij is the utility row player gets by playing I, and when the column player is playing J, and probability that they are actually playing. So, this word outcome basically what it means is that row player is playing ith strategy and jth player is playing the jth strategy. As before we said that whenever this sort of thing happens, we always assume that they are working independently. Okay. So, therefore, this definition basically this joint probability gets split into a product of the two individual probabilities, and that is the summation you get. Okay. Any questions? Okay. Now, okay. So, now okay.
How do you interpret that? The quantity of
Okay. It means that whatever this is the left hand side, this has the right hand side, right. This left hand side tells me what should be the optimum solution for the row player if row player goes first. This tells you what should be the outcome of the row player if column player goes first. They happen to be equal. So, no matter who goes first, right, this would be the value attained when both are playing optimally, like the way we argued, that you know what you understand what the other person's response would be, therefore, you play a strategy that will basically maximize your thing, and the column player does the minimization thing. Okay. So, this value, this common value is often called the value of the game, okay, and we will see how what it is and so on and so forth. It does not have to be. Do you want to take a guess what should this value be?
But like just trying to interpret just from inside out, you minimize over y, but like what are you minimizing?
I am minimizing this quantity.
But
So,
there's an x also.
yeah. So, think about I enumerate, I pick an x, I find the y that minimizes that x transpose a y. Yes. Okay. Okay. This is a good point. Okay. If this is not sort of clear, you for given x, can you see? I can't move this. Okay, I'll write here. Yeah, you ask the question, so you get the first privilege to see. Okay, given x, find the y, which does what? Tell me.
Minimizes.
Yes. So what? Let's say. Correct. That's for you, right? Now you define x hat to be 1 where this quantity is the larger, the x that gives the largest possible value for that. That is what the row player would do, right, because he knows the column player will respond with a minimizing y. So, I will pick that x for which that minimizing y, no matter what, is as of highest value as possible, right. So, the other side makes sense.
Yeah, same thing.
Same thing, right, symmetrically opposite kind of a argument, except that the column player is going first. Is it okay? Okay. So, this is nothing but what we were just discussing. I see that the expected payoff for the row player, even when a mixed strategy is played, should be this. This summation I is indexed over the number of rows, this is for the number of columns, Aij is the ijth entry of the payoff matrix A. This is probability row I is chosen, probability column J is chosen. Now, this if you unravel, okay, just if you write it down, you will see it actually comes down to x transpose A y. Okay. So, computing x transpose A y actually does give me the expected payoff of the row player. Okay. All right. This has a semantical issue. So, do you see where what this issue is? Is it correct, the last two things? Payoff of row player with respect to what? Payoff of row player with respect to x and y. Remember that we wrote this in the previous slide. When we compute an expected payoff, we are always talking in terms of a mixed strategy distribution, correct? Here the mixed strategy distribution is a pair x and y. Over there we had an n length vector because we had n players, right, that x1, x2, xn. Here it is an x and y. So, even though it is not written here, it should be implicit that we are talking about strategy x played by player x, row player, y is the strategy played by y player, and then this is correct. Okay. And row I is chosen. Where will I get this value row I is chosen? I basically look at the probability density value, mass function values of x, right. I basically look at ith entry of x, jth entry of y. Okay. Okay. Before I will post all the slides, I will make these corrections. Okay. So, Sanjay or whoever is listening, you will have to check if all the corrections were made based on all the typos. And
Zero-sum game is not limited to just 2 players. Like it can have.
Yes, it can be. This theorem works for 2 player zero sum games, and you will see the technical reason why. That is a good question. Zero sum game has nothing, it does not have to be a 2 player, you can have a 3 player thing, right. So, and that constant sum game is basically you can have multiple player, they just all add up to some precise fixed constant. It is like a prize, you have this much of prize money and it will be split among maybe 3 people, 4 people, that sort of thing, first, second, third, that sort of way. Okay. Okay, this actually came last. Okay, I thought I had completely missed out this, yeah. So, the slide is not entirely wrong, it is just the order in which things appear. Okay. So, naturally the expected payoff of the column player is minus of this. Okay, everything just jumped out. Okay. So, now we will prove this. How am I doing time wise? Okay, good enough. So, we will prove this. Okay. We will prove why this is. Now, let me just ask you, just looking at it, when we show something to be equal, it is enough to show one side is less than the other, less than equal, the other side is also less than equal to the other, right. So, in this, is there a simple straightforward relationship you can infer? Left hand side, the maximizing size should be greater than the other. Why? Because max is written, but it is also equal. Right? So, I am asking you to reverse engineer a proof. You know, suppose this is true. It is like a homework exercise. So, you know the statement is true, not an open question. So, then how would you make a first pass at it? Okay, we will come to this. Okay. One side seems to me is much more simpler to argue one direction of the inequality than the other. Okay. And we will see why maybe. You can think about it and you can let me know if you know. So, we argued this before, second player does not actually has to randomize. Whoever goes first, row player goes first or column player goes first, the second player can always respond with a precise choice. Over here, our choices actions are basically corresponding to columns or rows, right. So, if the row player goes first, then the column player should respond with a column vector. So, A E J, E J is the standard basis. What this means is A multiplied by J is basically it will extract the jth column from A. Okay. So, if row player plays X, column player should respond with the jth column of the matrix A. Why is that correct? At least it should be clear that the column player, therefore, there must exist a column which will give him the minimum outcome, right. Over here, you can pick the column, right, that gives you the smallest possible value.
Yes.
Is there any reason for me to mix it? Like, is there any reason to take like two different columns and take variable this thing? Try to convince yourself of this. Okay. It's a bit of intuition, maybe math, but okay, at some point both things will match. Okay. So, this is the thing, that if whatever this is, if you can, this person can always respond with a unique, not a, there can be multiple columns choices, he will respond with one choice that gives him the minimum, for which this value gets minimized. Okay. Okay. So, the left hand side, row player is going first, is the what the left hand side says, right. So, the left hand side basically is equal to choice of the smallest value column, or I should not say smallest value column, a column you run over all the possible columns and you pick the one for which this X transpose times the jth column is minimum. Okay. That is what this is. Now, this is actually equal to this. This is just multiplying, just it is a dot product, right, correct. Okay. I am sorry, all this extra stuff, it should not have come in this thing. So, you agree that this is equal to this, right. Notice something, this is a linear function in what? X I, right. A I J's are like coefficients, right. The X I's are, this entire expression is basically a linear function in the X I's. Now, there is a bit of a weirdness in the sense that I do a linear function here and then I am doing a minimization projection, right. But I am talking about only this part, this dot product part. Okay. Okay. So, do you think this can actually help us in some way? At least those of you who have seen LP formula, if you have never seen it, it would be remarkable if you can infer what should happen next. But those of you who have seen this sort of framework, can you all like in sort of make some educated guess as to where all of this is going? Okay, let's see one thing. Okay, so this is the to prove this thing. What I am going to argue from the left hand side, these two things, as we agreed, this one shows the row player going first, what happens, and this is when the column player goes first. This left hand side tells me how to reason about the row player going first. Similarly, there is a argument to be made when the column player goes first, which will give me the right hand side value, right. So, the proof of this would be to show that the quantity that emerges when we argue for the column player side is actually equal to the quantity that has emerged when we argued for the row player going first, right. That is a sufficient, that would be a sufficient condition. Okay. So, now those of you who are, because this proof has a linear programming this thing, so I kind of have to lead you towards that. But there are a lot of arguments here which do not require you to know that this formulation. Okay. But one thing you can see that in order for us to be able to use LP duality, we need a linear program, right. The constraint space should be linear, and the objective function, strictly speaking, it does not have to be linear, but I suppose most of the things that you may have seen are linear objective function. So, let us say that is the case, but a linear program does not even need an objective function, strictly speaking. All we need is a bunch of linear constraint, and all we ask is there a solution that satisfies all this constraint? Okay. That is a general, that is a requirement primarily. Now, here we see at least this tells me has a natural maximization aspect to it. We are trying to find an x that maximizes over something, right. So, it seems like we are on the right track of LP, maximizing LP. The problem is this nested min. Do you know how to get rid of this sort of a nested min? It is a trick basically. I mean, it is not very complicated or anything. Once I tell you, you will say, aha, but that is the thing. You can use this quantity itself as a variable and say, I need a value v, right, which is no bigger than this, it remains as small as possible, and then make that your objective function. You want the smallest possible a maximum v such that v never exceeds this quantity for all j's.
So, basically we convert v greater than equals to this into constraint.
V greater than equal to, you want v to be, this is the minimum thing, right, minimum, meaning v will always be at most this quantity, v would be at most this quantity for all j 1 to n, and you want to maximize that v. Okay. So, let us see, otherwise I will write, I am sorry, everything just came in. Okay. So, yeah. So, this v is that object, there was a layout. Okay. So, v minus summation of aij xi less than equal to 0 only means v is less than equal to summation of aij xi. This was the quantity that was inside that bracket, right, and I need this condition v to be less than this for all the columns, because we were minimizing over the column space, right. But the row player was doing a maximization of x for that v, therefore, max v is the objective function. What is this constraint? Summation of xi being equal to 1. Yes, because we are not talking about any xi, like just arbitrary vector xi, vector x. We need it to be a probability density function, right, it wants to be a distribution, therefore this, correct. Now, x1 to xm, the individual values of the x probability vector, they should be greater than equal to 0. I do not have to write at most 1, why? Usually probability is always defined as greater than equal to 0, less than equal to 1, but over here I do not need to write greater than 1, because of this already, it is already equal to 1, right. So, nothing, I mean, if one of them is 1, it can't go beyond, none of them can go beyond 1 because there is no negative values, like positive non-negative numbers cannot add up to 1 if any one of them goes beyond 1, right. So, that is the thing. Okay. Is it clear how I extracted a linear program from that constraint, from that condition, right. So, this is what one would call is a linear program. All the constraints are linear and you have some maximization objective function.
Why do we want v less than equal to? Can't we just take equal to v equal to?
Because of this, you are trying to find a v, max v, right. But what is inside here? We are trying to do minimization. We are looking for a j column, a column j, such that the summation of xi aij is minimum, correct. So, if you tabulate all the possible values, xi aij for 1, xi, this is a problematic thing. I think m, okay. This is for column 1, okay. Then xi ai2 this is an n value set. I mean, they might be duplicates and all, but at most this thing, right. So, what is this doing? It is a minimization projection, right. It will pick up the minimum value. V is a variable which does just that. So, V must be at most each of this. So, therefore, summation xi aij, this summation goes from 1 to m exactly for all j from 1 to m, 1 to n.
Equality will also lead to same.
It is okay, but for if V, the minimization is this thing, all these are larger, then this can't be equal, no. Less than equal to means equal or less. If there is a unique minimum, all other values will be strictly greater. Then writing equal prevents me from like capturing that condition. Okay? Okay? So far, all right. So, this is what gives me the this LP. Okay. Now, what is the optimum solution? So, an optimum solution for a linear program is basically a feasible solution. Over here these are the variables. So, you need to tell me what should be the values assigned to this xi to xm and v. So, there are m plus 1 variable in this program, okay, and that will basically tell me whether, and if that satisfies these conditions, that would be a feasible solution. Now, there could be multiple feasible solutions. Now, you want to find the feasible solution which maximizes this objective function. Okay? The x star, the feasible solution x star that gives you the maximum value for this objective function is what constitutes the solution here. Okay? This is an m plus 1 variable program. So, we have m plus 1, x star basically encodes in it all the x1 to xm and then v star. Okay? Okay. Clearly, we agree that by the definition of optimality, v star should be equal to this, right. It is an absolute equal minimum and so on and so forth. That is what I wrote there, right. Okay. Now, okay, I said it, the linear program basically will try to, it is going to look at over across. So, each valid assignment to xi's gives me a mixed strategy for the row player, correct, and the linear program tries to find one which would maximize this value v, right. So, if you think about these values as being on the number line, okay, somewhere, v is trying to move and the minimum somewhere lies here, okay. So, let us say this is the minimum, this is where they lie, okay. V always remains behind this, and you want to see how far we can go. So, we can basically come as close to this. The V that actually gets all the way to here is my optimum solution, correct? Okay. Therefore, do you agree that no matter, so I choose the column j that minimizes the answer response game. V star is basically attained by that value. So, x star is one solution for which V star is the optimum value, but more generally we can say that V star must be a value such that the maximum I can push V so that it remains behind this value is the optimum V star. And now the question is, why would I leave a gap here? Does that make sense? I might as well be exactly equal, right? That is why you get equality.
So, x star is the optimal strategy that the player should choose.
X star is a solution, optimum solution of this linear program. We are now trying to see how does x star and V star behave. By knowing that V star is an optimum solution that satisfies this constraint, we know V star is always less than equal to this, but there is no reason to be strictly less than. V star might as well just be equal to this minimum value. That is what this is saying, the last thing. Okay? Yes, that is the thing, there is no reason to leave a gap here. Why stop it? Push a bit more, you will. If you leave a gap, that can't be the optimum, because there is a value which is delta slightly more than this, which will give you an even larger optimum value. Okay? All right. So, I wrote this here. Okay? I will analogously argue the same way with the column player going first, and I promise you, if you think similarly, you will get a program which looks like this. You have minimization of W, where W is now basically at least more than this, because what does the column player always try to do? If the column player is going first, he understands that I should pick a strategy that will minimize the W's payoff, minimize X row player's payoff, right. So, therefore, this is the W is the thing, and right, this thing, is it easy to see? Okay, I will write. So, row, I will just write here for completeness, column player going first, what should he pick? He can look at, he knows no matter what I pick, this row player is going to respond with the row that will maximize his outcome, correct. So, then if column player goes first, he can, for every y, he can see what is the least EI transpose A y, right. So, he can take the argmin of this, wait, let me think. for a given y, he can compute the argmax y. Okay. This would be the choice of the row that will enable the row player to get the maximum value. So, he should basically pick a y that minimizes this quantity, right. So, this is why w, this w is this quantity which is always choose an y minimizes value of x. Okay. The value of x is this thing. Therefore, this quantity I am going to make a mess of. This is correct, no? Sorry. Aij yj, correct? J. Yeah, 1 to n, right. So, this is that variable w, this is max, achha, yeah. No, sum should be over I, yes, correct, yeah. Is it? No, it's a max is over, yeah. Sorry, yeah, that's why semantic, it doesn't make sense for us. J equal to what? 1 to n, right? This was m. Okay, sorry. Okay. So, this the variable w is basically tracking this quantity. So, you want w to be at least more than summation of aij yj for all I. That is what this program is. Everything else remains the same. See, probability density function, blah blah blah, all those things. Now, similarly, suppose w star y star is an optimal for the column player. Then what can we say? Similarly arguing, we see that this is true. It is the same idea. Why leave a gap? Except that now, let us use a different color. Okay. This was the tracking line for V. Now, what should W do? W is at least this much, right. So, this is let us say the max of this summation of the aij yj. W is basically here, correct, but I have to minimize W. So, I will get as close to this as possible. In fact, I will basically reach this point, correct, because W is more than summation of aij yj, right. So, this is the maximum point, this is that quantity. So, W is basically here and it is a minimization. So, it is coming back. So, this is a real line. Okay. Now, these are two quantities. Now, linear programming duality, this is where the frame, so far we did not actually use anything about linear programming formulation, but here if you know how to work with linear program, you will see that this program and this program are intrinsically related. They are the primal and each other's dual, like they have the primal dual relationship. Okay? And when programs have this relationship, we know that the optimization value for one, optimum value for one is equal to the optimum value for the other. Okay? That is why, that is what gives us that V star is equal to W star. There is a notion of weak duality which says that when two programs have this primal dual relationship, the maximization quantity, okay, that sort of that was the thing that I was asking, the maximizing program this sort of feasible values are always lagging behind the minimizing program's feasible value. Sort of if you think of it in terms of so on the real line, what that means is these two programs are related. The maximization program is trying to go as much as possible. The minimization program is coming down, is trying to minimize as much as possible. If at strong duality we know that the optimum must be equal, so it must mean the all feasible solution for the maximization problem are at most the feasible solution of the minimization program. Okay. So, this is weak duality. We do not need weak duality here, we just use strong duality to infer that V star is actually equal to W star. Okay. So, what did we show? Basically, we showed this quantity is equal to this quantity. Okay. Any questions? Now, let us get back to that question I asked. Suppose you can't show equality without using LP duality. Can you still say some inequality between, like some relationship between these two things, left hand side and right hand side? Okay. So, do an exercise. There is a nice way of saying. Okay. Do you have any examples for zero sum game where they can actually compute this and see which is one thing is less than equal to the other and so on? Okay. So, I will tell you that this side is at most this side. But probably not. So, the point is, among all the, it is very much again uses intuition from weak duality. So, it is very biased. It is not a clear just argument where it shows, okay, let me just think about, I will try to give you a, I think there is a way of explaining this where you should be able to see why this is at least at most this. The other side requires some other argument. This proves uses this the strong duality gives it. There are other proofs that they are using fixed point and so on where this. So, in order to establish the one side is easier than the other is the bottom line. Okay. So, but I can't quite describe it without somehow invoking this. So, I will just leave you all with little just one more thing. Okay. Linear programming formulation are incredibly powerful. I mean, they are incredibly versatile in how many things we can sort of give. Okay. And the relationship that we basically, I just put this thing together quickly. This can't be a class on LP duality because like that would be well beyond the scope, but basically programs that look like this, they are supposed to have a primal dual relation. This is a maximization, it was a row player thing that we were doing. This was the constraint space, right. We were tracking V on this side, we were maximizing V, we are tracking V, plus there was the probability distribution summation equal to 1. So, this is why less than equal to allows you to encode equality constraint. Here we were tracking W, which was a minimization value, minimizing thing. This again was capturing that tracking this thing that you are you want to be always be greater than this, the max of this and also the equality allows us to capture the yi. Okay. This is a constraint that says that y these variables, y this is a matrix again, these y variables are non-negative. Okay. Here also we had the same thing because we are dealing with probability density functions, right. We were xi's were representing probability values of certain actions being taking place. And this is basically the duality theorem. Now, you do not have to read this, but if you knew it, you would be able to sort of infer a lot of different properties about programs which have this relation. In short simple words, if we can solve an optimization version of one of this, we basically have the optimum solution for the other for free, because the optimum solutions are equal. We also have the relationship that this any feasible solution, the z value will be at most any feasible solution of this problem and its optimization value. So, you basically get a bound, okay, that this one cannot be more than this, and that sort of thing allows us to do algorithms or analysis in a sort of you are not like running across the entire number line. You know that there is a bound there and the value cannot exceed this. Okay. All right. So, I think I will leave here unless you have any questions.
So, in that min-max theorem, I could understand the LHS properly, but in RHS, so we were saying that the column person will go first.
Yeah.
Like, can you once explain it? Like, so column person is going first, and it knows that after it goes first, the row person would try to maximize its own utility.
Yes.
So
what should the column player do to maximize his own utility?
So it will minimize the other one.
Yes.
But the same logic we can apply to the row person going first. Like row person is going first, he knows that the column person would try to maximize his own thing.
Yes.
And it would then minimize it. Like.
Yeah, that's exactly what we did. The argument is entirely symmetric. The point is, what else are we doing here? The row player knows that if I go first, column player will always respond with a y that will minimize my payoff.
And maximize its own.
No, minimizing row player's payoff automatically means maximizing the column player's payoff. So, the column player always just has to think that I have to keep the row player's payoff low. That because it's a zero sum game. That automatically means that my payoff would be maximum.
Like anyone who goes first.
Yes.
Will use the same strategy, right?
Whoever goes first will think will choose something so that my payoff is maximum. That is true. In the case of the column player, that just means keep this x transpose a y quantity small, because A represents the payoff matrix for the row player. In other words, whatever this value is, x transpose a y, column player's payoff would be negative. So, this is true, they are all arguing the exact same way, but one person is trying to maximize his outcome, right, and the other person is trying to minimize that.
So, if we
minimize the
minimum of y and minimum of in the second half, the RHS, we write maximum of y and minimum of x.
If I write maximum of y and minimum of x would mean what?
Like same, the y is going first and
minimum of x?
Yes.
This thing, right? Right? So, y is choosing a column vector that x, no matter how poorly he plays, the row player plays, will give him will create the largest possible x transpose a y value. That, sorry? No, but he didn't say that. That's why I am trying to say that why this is problematic. Right? Because the column player y.
That's how we have defined that A.
Yes. This is why I keep on saying that it's important to note that x transpose a y is capturing the payoff of A, of the row player.
Yes, row.
But that, because it's a zero sum game, that automatically fixes the payoff of the column player. So, column player's goal is always I will keep x transpose a y as low as possible, whether I go first or last.
Yes.
And row player's strategy is to maximize this x transpose a y quantity, whether he goes first or last. Okay? Okay. So, I will, so I just want to say that it was, I already said this was original proof, this idea has been discovered again and again. I mean this sort of it has been rediscovered in many different contexts. Danzig, there are very interesting story of Danzig interacting with von Neumann. Von Neumann was thinking, had an idea what duality theory was discovered by Danzig, but von Neumann had sort of already started the mathematical work on game theory, and he was sort of proving these results sort of in a discrete sort of different way. There was no underlying at that time theory which bound everything, but over time these things started emerging, and I think von Neumann saw the sort of multiple secondary proofs of this zero sum minimax theorem in his lifetime. So, but this happened decades later. Okay. LP linear programming is a very powerful framework for designing algorithms. This was just a very small, simple, very cute exposition of it. If you do not know, I would highly recommend you studying. There are lots of video lectures and so on and so forth, and good textbooks on it. Okay, there was something else here. Now that didn't come. Okay, so then I'll leave you with that. Okay.